Okay, so I'll introduce François, and then he will present us his work. So yeah, the reason I'm so interested in François' work is that this is, to my knowledge, either the first. I mean, there have been attempts to develop non-equilibrium thermodynamics, but one of the only attempts to derive it from variational principles, which I think is the only hope, or the best hope, to have a complete theory. And as we talked with François earlier, the stumbling block is that has been that people underestimated this approach, because usually the Hamiltonian mechanics and Lagrangian and least action principles have been used in a sense of conservative systems everywhere in physics. So when people see dissipative systems, irreversible thermal, and not even thermodynamics, just dissipative systems, they don't use it. And of course, it's not developed for dissipative systems. So what François has done, with collaboration with Hiroki Yoshimura from Japan, is I think heroic, overcoming this difficulty and expanding to dissipative systems, and then going into non-equilibrium thermodynamics. I will let François take it from here, but he is at, as you can see, École Normale Supérieure de Paris. So without further ado, I will give the floor to François, and I'll be happy to hear more.
Thank you very much for the introduction. Thank you. So yeah, for me, it's a great challenge, right, to speak to such a wide audience. So as it was said in the introduction, my goal is to present some recent progress in the establishment of a variational formulation for non-equilibrium thermodynamics. So 2 points before I start is that this approach that we developed should be seen as an extension of Hamilton's principle of classical mechanics. So this is the origin of our development, right? We wanted something which extend classical variational principles. And also I will illustrate a little bit why this can be useful. And also to make things clear, where we are so far is in the setting of macroscopic description in non-equilibrium thermodynamics. That's where the development of variational formulation is so far. So we hope we can make some progress also on further going into the mesoscopic or microscopic description, but so far I will only discuss the macroscopic point of view. And my goal is to see how this variational principle unify the picture one can have about thermodynamics. So that's the plan of my talk. So the first part is very, very classical. It's just to be sure that we speak the same language, right? I will recall the well-known action principles in physics in various areas. Then I will spend some time to describe very briefly non-equilibrium thermodynamics. Then I enter the main content of the talk. And I will start, for pedagogical reason, with finite dimensional and adiabatically closed systems, right? The easiest one. Then I will increase the difficulties. I will go to open systems, still finite dimensional. Then if time permit, I will also comment on continuum systems like fluids, etc. Okay, so to clarify the foundations, let me just give some words on the critical action principles in physics. So it's an important observation, right, that a lot of equations in physics, I mean, the most important equations, in fact, can be derived from a critical action principle. So if we think about classical mechanics, for instance, particles, fluids, and solids, then the Newton's law for these systems can be derived from a critical action principle. So how does this work? So if you have, for instance, one particle in a potential, V of Q, you have a particle of mass M, then you build the Lagrangian of the system, which is the kinetic energy minus the potential energy, and you build an action, which is a map defined on all possible curves of your systems, and you integrate the Lagrangian over this curve, Q of t, right? Which is not necessarily a possible motion, but any trajectory in the physical space. Then Hamilton's principle tells you that the actual motion of the system is the curve that is critical for this action functional, right? So one writing is this, another one is just the usual classical Hamilton's principle, in which you take variations of your Lagrangian. So for future reference, I write here that the set of all trajectories that we take when we compute these critical points, then they are really in the physical space for these simple examples. And you will see it's not like that in more general systems. So since I will extend this in various ways, I present the computation to be sure that we understand what we mean here. So when we take the variation of this action, right, we have two terms, the kinetic energy and the potential energy. And we integrate by part in order to isolate the variations of the curve, right? And we get this first term, which is the main part of the derivative of the action, and a boundary term, which is just the momentum evaluated on the variations. Now, if you assume that the initial and the end point of the curve are fixed, then the variations of this curve at the initial time and the last time vanish. So you get this, and you get the Newton's law for this particle. So this is extremely simple, but in fact, all my talk will be about adapting this simple computation to non-equilibrium thermodynamics. So in a more abstract way, what we have done here is we have written an action, right, a functional, on a space of curves, which are all possible curves in the physical space with fixed endpoint at initial and final time, with value in R, right? And we have computed the critical curves. Another example that is a little bit more involved is the case of rigid bodies. So in this case, what plays the role of the point Q of t of the previous example? So if you think a little bit, you realize that a rigid body is like a frame, right? So if you want to indicate the position of this frame, it's enough to have a rotation matrix. So Q of t of the previous example is now given by a time-dependent rotation matrix. So as before, I can compute the action functional, which is simply the integral of the kinetic energy of all the rigid body particles. So I name them x. So it's the integral of the mass density times the velocity of each of these rigid body material points square, right? Integrate over the body. And I get the Lagrangian in principle, right? L of the position and velocity. And then this is not so practical, but it can be converted in terms of the angular velocity, right? Omega, which is defined in terms of the rate of change of this rotation matrix. And this is the familiar body angular momentum. And now the question is, what is the Hamilton principle for a rigid body? So answer, it is the same as for the point particle, except that your curves are no more in the physical space, but they are in the rotation group, right? That's the only difference. But abstractly speaking, it's exactly the same principle, right? Hamilton's principle, but written on the Lie group of rotation matrices instead of written on the physical space R3, right? So in particular, you have to be careful when you take variations of a possible rotation matrix, not to add an arbitrary rotation, because you will go out of the group of rotation. So now you have to stay in the rotation group. And you get the Euler equation for the rigid body, for instance. So this is just to say that Hamilton's principle can be really applied to a lot of examples. Is one looked right at what are the curves Q of t that one has to consider. Another interesting example is the case of fluids. And this is important for the next part, the last part of the talks, in which I will introduce extension of this to thermodynamics. What is the curve Q of t in this case, in the case of fluid? So for fluid or continuum mechanics in general, what you need to describe the motion of a body or a fluid is a fluid configuration, right? It's a map phi, which gives you the position of each fluid particle at some time t with some label x, right? X is the fluid particles and x of t is its current location. And this map phi, we can assume, it's not always the case in reality, but we can assume formally that it's a smooth and invertible map. So it's a diffeomorphism. Then, without entering into some details, we can write exactly the same type of action functional. We take the Lagrangian of the fluid, but Q is now a fluid flow, right? Such a map phi that I described earlier, and phi dot. And you write here inside the total Lagrangian of your fluid system, right? The kinetic energy, which is the integral of the kinetic energy of each fluid particles, and you subtract the internal energy. You can choose here your preferred state equation or stored energy function if you are doing elasticity or any other potential energy. In general, can depend on the fluid map, the gradient of the fluid, and the mass density. If you do the exercise of computing Hamilton's principle, then after some quite long computation, you get the fluid equations. For instance, here I wrote the Euler equations, but you can also get compressible Euler or magneto-hydrodynamic equations and other type of fluid, as long as you restrict to reversible motion. Then some other examples, they are just, I will not enter too much into the details, they are just there to tell us how practical is the critical action principle. For instance, if you do electrodynamics, you have one action functional for the charged particles. For instance, here it's a particle of mass m and electric charge E moving in an electromagnetic field with potential A and phi, right? And you build your Lagrangian, take variations, you get the motion of the charged particle in the given field. Now, if you do the same thing for the fields, right? You write the Lagrangian for the electric field minus so square of the electric field minus square of the magnetic field, you get your Lagrangian. Compute the Hamilton's equations exactly as earlier, you get the Maxwell equations. Then if you want to couple them, it's also extremely simple. You just add the two actions and it directly gives you the correct equations, namely Maxwell equations with the source terms together with the motion of the charged particles. Another example is also general relativity. Same thing, right? What I said earlier also applies to this setting. For instance, if you consider one relativistic particle moving in a space-time with a given Lorentzian metric G, for instance, if you look for the our critical action principle for the motion of a mass particle in the vacuum, then you consider this action functional, right? Square root of minus the square norm of the velocity multiplied by the mass at rest and the squared light velocity. And you get the geodesics. And now if you want to know the equations for the Lorentzian metric itself in the vacuum, namely Einstein's equation, again, you have also a critical action principle, which is also extremely natural once you know pseudo-Riemannian geometry, right? It's just the integral of the scalar curvature of the pseudo-Riemannian matrix. A last example is also quantum mechanics. Maybe it's a little bit less well known, but the Schrödinger equations also have a critical action principle, which is the Dirac-Frankel action principle, and which is in some sense related to the phase space principle of classical mechanics, and which takes this form. And again, critical point condition for this action functional will give you the Schrödinger equations. Okay, so this was a little bit fast. It was just an overview to recall how complex and important equations can be formulated using relatively simple, in fact, action functionals, at least for those examples. And as I said, each time this functional is physically meaningful, is not a made-up expression that we have to derive in such a way that we find a given equation. No, no, it's a physical meaningful functional that gives the equation we want. So it's very useful to unify various areas of physics, and also to derive equations that would be very hard to derive without such a variational formulation. And another aspect that I will not discuss is that these critical action principles also have associated geometric structures. For instance, Poisson brackets, symplectic forms, or more general structure that can be derived also from the critical action principle. Also, the famous Noether theorem can be derived from action principle simply by taking variations of the action functional along the symmetries of the systems. And the answer then is no more the equations of motion, but the conserved quantities. And that's what Noether originally did, right? She really did this computation. So if you are interested, maybe you know some good books like Langchos or more recent Cooper-Smith that discuss various aspects of this critical action principle, also others, not only Hamilton's principle, and also some more philosophical comments about the existence of such principle. Okay, so let me now say some comment about the field variations. So far, I computed critical point of some action functional, but I never said what variations of the field I consider. So this, for this talk, is a main point, right? So when I compute delta A for some field in a huge space of fields, what set of variations do I choose? So in fact, what I did so far, I choose all the variations that are tangent to the space of field that we consider, right? So for instance, if we fix the initial and the end point, the variations at the initial and the end point vanish. Same thing, if we assume the field is known at the boundary of the domain, then the variations has to vanish at the boundary of the domain. So this is the classical setting for critical action principle. But now we go to some different perspective. In fact, important physical systems need restricted class of variations. And this is what I will have for thermodynamics. But let's not go there so far. And let's stay in mechanics. If I consider non-holonomic systems, for instance, a rolling ball or a rolling skateboard like this, these systems do not fit in Hamilton's principle because they have constraints. So, for instance, here the ball has to roll on the ground, right? So there is a constraint on the velocity, which is in fact linear, right? So we can write it like this. It's a linear constraint on the velocity, which may depend on the position, but linear in velocity. And D'Alembert proposed that the equations of motion for such non-holonomic system should be obtainable by a kind of Hamilton's principle, but in which the variations are also constrained in the same way as the rate of change, right? So the variations that you consider in the Hamilton's principle obey the same constraints as the velocity, right? And D'Alembert principle indeed reads like this. So it's Euler-Lagrange paired with variations has to vanish, not for all variations, only for those variations that satisfy the constraints. So this is a key difference with Hamilton's principle. More precisely, here I'm writing formulas about what I said. So the action is still the good old action functional of Hamilton, but now the computation of critical points is subject to two constraints. A constraint on the solution curves, right, linear in velocity, and a constraint on the variations, linear in variations. And what you get are the so-called Lagrange-D'Alembert equations, in which this is not zero, but it's some formula that depends on the Lagrange multiplier. And you have the Lagrange multiplier, the constraints equation to solve for the Lagrange multiplier. So you have a complete system to solve the motion of the rolling ball, for instance. So very important, this is not a Lagrange multiplier critical action principle. I'm not adding the constraint to the Lagrangian and taking the variations. That's not what Lagrange and what D'Alembert did. What D'Alembert did is computing the variation of the action functional, and then assume that these variations are constrained, which is not the same thing, right? So this has an interesting history, in fact, some controversy also, that you can learn more in these works there. So now let's keep this in mind. So Hamilton's principle and Lagrange-D'Alembert principle, and say some words on non-equilibrium thermodynamics. So first, equilibrium thermodynamics. So as you all know, this is only about equilibrium states, right? And quasi-static processes. And the math behind equilibrium thermodynamics is quite well understood, right? It started with Gibbs, and it is more or less use knowledge of differential forms, and I would say it's enough to understand equilibrium thermodynamics. Of course, equilibrium thermodynamics applies also to problems that are a little bit outside the equilibrium thermodynamics. It's still very useful, but it's useful as long as we don't care about the dynamics that the system has between the two equilibrium states. Now, non-equilibrium thermodynamics, so here I write some founders of this field. And as I said, I will focus on the macroscopic descriptions only for system out of equilibrium, but I will allow the system to be, for instance, open or connected between themselves, etc. But I assume local thermodynamics equilibrium. This is very important. So here I'm just writing down some notations that I will use later for future use. So first, I recall the two laws of thermodynamics, right? So there are lots of formulations. The one we found it very useful were the ones by Stuckelberg, right? That you can find in a book by Stuckelberg and Scheurer, which assert that, as you know, there is an extensive state function, the energy, that follows this balance, right? So here on the right-hand side, you have the power, external power due to work, heat, or matter exchanged with the exterior. And the second law that tells you that there is an extensive state function, the entropy, that must increase as long as the system is adiabatically closed, right? Often I will use this notation for internal energy with temperature, pressure, chemical potential. These are the typical irreversible processes that I will treat in these lectures. Also, it's good to remember that entropy production, it's a sum of terms. Each of these terms, it's a flux times a force, right? This will play a main role also in the variational formulation. And I will use so X alpha for the thermodynamic force, that are some universal quantities, and the J alpha for the fluxes that obeys some phenomenological expressions. So this is just to set the notations. Now some elementary examples that I will consider. So I will start with the simplest one, which is a thermo-mechanical system, in which your state variable is just one length, right? The position of the piston in this case, and one entropy, which characterizes the state of the gas inside the piston. And you will see that devising a variational formulation for this problem will help us go to more complicated problems, like for instance, diffusion of a chemical species through a membrane. So here the state variable are the number of moles in each locations. And I can assume here for simplicity that there is one single entropy variable in the system. Other examples that I will consider are chemical reactions. Right, so here I denote by A the chemical substance, nu are the stoichiometric coefficient, and I will show how the evolution equations for this system can be also derived from a variational formulation. Another kind of systems are those with several entropies, which are also quite interesting from the point of view of the variational formulation, in which, for instance, you have two compartments exchanging heat and matter between themselves. So that's one other representative system that we will consider. Other ones are open systems. For instance, this is a system which can exchange heat, matter, and also mechanical energy with the exterior. So it's like the previous one, a piston, but in which you have some ports now. And some other systems also that frequently arise in biophysical systems, in which you have several compartments exchanging matter and heat, and also with the exterior, right? So for such examples, for instance, the thermodynamic forces are the chemical potentials and the temperature of each compartment, and the thermodynamic fluxes are the entropy flux and the matter flow rate between each of these compartments. Finally, some infinite dimensional examples that I will also mention is the case of the, for instance, here I chose a multi-component fluid with heat, conduction, viscosity, and chemical reactions. So in this case, you have these kind of systems. So this is the usual Navier-Stokes equation. Here you have a reaction diffusion equation for each of the species. And here you have your entropy equation. So I will show that this set can be obtained as a critical point conditions. So we have already seen in the introduction how the red terms can be obtained by critical Hamilton's principle. So I will show how the blue terms can be also added. Right. So this is this will be an extension of this principle here. Okay, so let me start now with the simplest case. So that's the case of a thermomechanical system. So assume we have a Lagrangian. So this Lagrangian depends on velocity and position as before, but also now we allow it to depend on the entropy. So we have kinetic energy minus potential energy, in which this potential energy can depend on entropy and position, right? So in this case, our formulation reads like this. So I assume also we have some external force and some friction force. So as I said, it's a D'Alembert type of principle. So we have a variational condition, right? A critical action condition, which involves the Lagrangian and the external force. But now it's subject to two kinds of constraints, exactly as in the D'Alembert approach. We first have a constraint on the curve, which takes this form, right? You have dl ds s dot, which is the contribution of the entropy in the Lagrangian, must be equals the power of the friction force. And here you have an associated virtual constraint, which simply replaces the rates of change by delta variations. So here you have some virtual variation, and here you have the virtual work of this friction force. So it's quite analog, as I said, to D'Alembert principle. And the equations that you get are a mechanical equation in which the friction force appears there, and you have a thermal equation in which the friction force also appears as a power that must be equal to the variation of the Lagrangian with respect to the entropy only. So you get a coupled system. And since the Lagrangian depends not only on mechanical part, but also on thermal part, this system is in general fully coupled. So to continue with what I computed in the introduction about Hamilton's principle, here I also give the computation of this principle to see how simple it is in this case. So you take variation of the Lagrangian, you get something like this, times delta Q, plus contribution of the entropy, delta S. Now you use that delta Q and delta S are linked by the virtual constraint, like in the Lagrange-D'Alembert setting, and you directly get the equations of motion, right? So it's crucial here to have variations that are linked between themselves. So let's very briefly see how the laws of thermodynamics apply. So your total energy has the usual expression, total mechanical energy. And the first law, you can directly see that if you compute variation of energy, you get friction force that cancel, and so you get only, as it should, the external power, which contributes to change of energy. Same thing for the second law, right? It's a direct computation that gives you the expression of S dot, and which implies that the friction force must be a dissipative force. Okay. So to come back to the space of path that I was discussing in the introduction, here this space of path is a little bit different because the red curve must fulfill the constraint, the phenomenological constraint, right, that I wrote here. I call it phenomenological because the friction force is entering the constraint. And the variations must satisfy these constraints, which is clearly associated by just changing ordinary differential by delta differential, right? So as I said, it's a D'Alembert type of principle. So here I just wanted to show how we can apply this to the piston. But this is exactly the same thing as in the abstract case. So I think it's not so useful. Okay, so now I'm coming to one of the most important slide, I think, because the question we ask is how to now incorporate other irreversible processes than just friction force, which was in fact easier. If, for instance, we consider diffusion, so we look at the thermodynamic force for diffusion, which is the chemical potential. And our idea was to introduce a thermodynamic displacement, W, that is such that its time rate of change is the chemical potential, right? So we want to make other processes look like if they were friction forces, right? Like if they were F friction applied to some Q dot. So here the Q dot for diffusion would be W dot, the variable that ultimately agrees with the chemical potential. If you now want to do chemical reactions, so you look at the thermodynamic force for chemical reactions and you define a thermodynamic displacement nu, such that nu dot is the thermodynamical force for chemical reaction. Same thing for heat conduction, exactly the same thing. You define a thermal displacement such that its time derivatives gives you the temperature of the system. So if you do that, you can derive equations of motion for general system in non-equilibrium thermodynamics by imitating what I presented earlier. So I give some examples. For instance, the case of diffusion between two reservoirs due to a membrane, for instance. So in this case, the Lagrangian has more variable because it has the entropy and the number of moles of each of these variables. So the thermodynamic fluxes are friction force like earlier, but also matter flow rate, which indicates here the flow rates between each of the compartments. And the variational formulation exactly take the same form as earlier, namely a D'Alembert type of form. You have here the mechanical contribution, which is friction force times Q dot. And you also have here the matter transfer contribution, which is instead of the friction force, you have the thermodynamic flux for matter transfer, which is the matter flow rate between each of the compartments. And Q dot is here played by W dot, which is the thermodynamic displacement for diffusion. Same thing, you replace time rates by delta variations, and you get the variational constraints. By this, I mean the constraints you use in the variations that you have to use in the principle. So if you do that, I don't go through the computation, you get the full system of equations for this problem. Namely, you have a mechanical part, possibly. You have here the equations for the balance of moles in each compartment. And you have here the equation, the thermal equation for the entropy evolution. And you get an additional equations which tells you that the variable W dot that you include in the principle turns out to be the chemical potential, right? Because in my variations earlier, if I go back, I introduced a new variable. So this can be bad if I have some new variables, but not, it's good because at the end, the principle also tells me that this variable is what I hoped it would be. I mean the chemical potential. Then you can proceed with thermodynamic phenomenology as usual. Just very roughly, this is another kind of system which now involve heat conduction. And so this time the thermodynamic fluxes are not only matter flow rate, but also entropy flow rate between each of the compartments. And the variational principle, so it looks technical, but it's the same thing again. It's a variational condition subject to a constraint on the curve solution and a constraint on the variations that you use. So for this example, you have contribution of heat transfer between each compartment and matter transfer between each compartment. And you have the corresponding D'Alembert virtual contribution on the variations of these variables, right? So there is something that I didn't explain, is this variable sigma here. So which is not S as earlier. If I go back earlier, I used S here, and here I use sigma. And you will need to wait that I go to open systems so that you see what is really this entropy sigma. Because at the end here, sigma dot turns out to be the entropy. So it seems that there is nothing new. But for open system, sigma dot and S dot will not be the same variable. So far, this sigma looks a little bit just a mathematical object that makes things work. But later you will understand it more deeply. Okay, so for instance, in this system, the irreversible process that we get are discrete versions of the Fourier and Fick laws, as well as the cross effect between these two effects, right? So, okay. So this ends the variational formulation for adiabatically closed system, and the general recipe is the following. So look at the thermodynamic flux, the thermodynamic forces, build the thermodynamic displacement, and then impose constraints of this type on the curves and on the variations. Now, as I said, most of the systems that we encounter are open, right? They can exchange matter, heat, or even mechanical energy with the exterior. So we were now interested to know how we can extend further this variational principle that I mentioned to the case of open system. So far we have seen Hamilton's principle, we have seen adiabatically closed system, and we will see how to extend it to system exchanging mass, for instance, or heat with the exterior. So that's as the simplest example is the same piston as earlier, but it can now receive heat from the exterior, right, at some given temperature TH. And so the Lagrangian, no change, is the same Lagrangian as before. So what I will now show you is how we can extend the variational principle to the case of open system. Then I will explain the nature of this variational formulation. So the critical point condition starts exactly as earlier. So it's a critical condition is in the sense of Hamilton's principle. But again, it has two constraints, one on the curve and one on the variations. The only difference with earlier is that here we need to subtract the contribution from the exterior, which is the exterior temperature, TH, that we use to heat the system. And you see that here the variational constraint is kept unchanged, right? TH does not appear in the variational constraint. So this has a deep geometric significance that maybe I can explain later. So now if you compute critical points, again, you get the equations of motion. So I don't explain them, except that now we clearly see the difference between the entropy variable and the sigma variable that I mentioned earlier. The difference is the following. Sigma dot is the rate of entropy production due to the internal process. So that's the sigma dot that must be positive from the second law. And S dot is the whole entropy change in the system. So you have contribution of the entropy flow rate. So S dot is of arbitrary sign. So this really attributes a clear meaning to this seemingly artificial variable that I had introduced earlier. So in the context of open systems, they are extremely meaningful. So now, for instance, I'm ready to link with the traditional notation from non-equilibrium thermodynamics. In my notation, the contribution to the internal entropy production is played by sigma dot dt, and the contribution to the entropy flow rate, right, is as it should, the entropy flow rate Js that appears there times dt. So this completely links the variable used in the variational formulation together with the more traditional thermodynamic notations, right? Then this is a slide just to illustrate that we can go to more complicated systems, like those systems which have a chemical reaction inside and also can exchange heat, matter, or work with the external world, like here, for instance. But this exactly works the same, right? So I will not go through this in details. So to finish open systems, the structure is the following. Assume we have some internal process, alpha, and process at the ports, beta. Consider the thermodynamic flux and the thermodynamic force of this process. Construct the thermodynamic displacements such that the time rate of these displacements are the thermodynamic affinities, and introduce the contribution from the exterior, if this is a process at the ports of the system, and then build this kind of constraints on your variational condition, right? A constraint on the critical point and a constraint on the critical, on the variations that you consider. So here you have contribution of the internal irreversible process, and here you have contribution of the process involved with exchanging energy with the exterior world, right? Okay, this is to relate with some more traditional notations. So I take the space of path like in Hamilton's principle, but now this is path in the space of sigma and lambda variables that I introduced earlier. And the constraints are quite natural, in fact, right? They involve temperature, internal entropy, thermodynamic fluxes and thermodynamic forces. And the dt contribution vanishes on the virtual side because variations of time are by definition vanishing. Okay, so we have completed this diagram, right, by including more and more complicated situations, and each time the variational formulation has the same type of form, but the constraint gets a little bit more complicated according to the fact that the system is closed or not, etc. Okay. Okay, so now I will jump to continuum system. So maybe I ask how much time I have to do this.
Yeah, I think if people don't object, I think we have enough time. Maybe another 10 minutes or so.
Okay, 10 minutes is more than enough. No problem.
Thank you.
Yeah. So as I said, fluid dynamics in the reversible regime also can be derived from Hamilton's principle. This is not so much well known sometimes, but this is true. The thing is that you have to work in the Lagrangian description of fluid mechanics. So you have to work with this flow map phi that I introduced in the introductory part. And so for single component fluid, you write the Lagrangian of the system, which is kinetic energy of the fluid minus internal energy. It looks a little bit cumbersome because I work in the Lagrangian description, but except this, it's the usual kinetic minus potential form. And importantly, for reversible fluid, the mass density and the entropy density are not time dependent, right? Because they are really attached to the fluid particles. So this means that when I take variation of the action functional, I only take variations of the fluid map phi. I don't take variations of rho and entropy S, right? That's very important. So if I'm doing now multi-component, I simply add as much mass densities as I have components, for instance, right? For a mixture of fluid, I will have here the internal energy of this mixture that I used in the Lagrangian, and so I can take variations. So if I do this, we get Euler-Lagrange equations for fluids, and they are not so practical, right? So I just wrote them for completeness, but it's certainly not the most friendly version of the fluid equations. So the one that we are usually see are the Eulerian version that I will show later. So, but the advantage is that when we look at fluids from the Lagrangian perspective, the critical action principle is nothing else than Hamilton's principle. Only you have to take your curve Q of t of particle mechanics to be now the curve phi of t of fluid flow. But except this, it's abstractly the same picture. So now, this is a technical side to tells you that if you want to apply the action principle in the Eulerian frame, it gets a little bit more complicated. It's not the goal to go through this. It's just to tell you that when you write the Hamilton's principle for fluid in the Eulerian picture, the variations that you have for the fluid velocity, the mass density, or the Eulerian entropy are no more free. But this is not the same kind of not free that I had earlier due to irreversible process. This is a constraint really due to the fact that we pass from Lagrangian picture to the Eulerian picture. So there are really two kinds of constraints here. And here in this slide, these are just constraints due to the fact that I work in the Eulerian frame. And if you do this, you get the familiar Euler fluid equations, right? Fluid equations, mass, continuity, entropy, continuity. So there is a nice geometry behind this process, which I will not describe, but which is really related to symmetries and the mechanical systems on Lie groups. So I reach a relation with a more geometric side of mechanics. So now coming back to thermodynamics. So I want to include now irreversible processes like I did for irreversible, like I did for finite dimensional system, but for fluid. So I will add those for principal processes. So I will imitate what we did for chemical reactions or for membrane transport. Yeah. So as earlier, we defined thermodynamic displacement, gamma, such that the time rate is temperature, or WA, such that the time rate is chemical potential, or nu, such that the time rate is chemical affinity. Then I apply exactly the same recipe. So in light blue, you have the variational principle for finite dimensional system that I mentioned earlier. So you have your critical point condition, and you have your phenomenological constraints involving friction, heat, matter, chemical reactions. In dark blue, you have the continuum version of this. So you can really see the analogy, right? Lagrangian is the Lagrangian. This variable don't change. It's just the number of moles becomes the mass density, the molar density, if you want. This term doesn't change. And here you add the processes: viscosity, heat, conduction, diffusion, chemical reactions. Some of them look a little bit unusual, especially viscosity, because I'm working in the Lagrangian frame. But this is the price to pay if I want to have a strict analogy with what I did with finite dimensional systems. Because if I go to the Eulerian picture, then I will have more variations to consider. Indeed, if I go to the Eulerian picture, I have this kind of formulations. So I don't go through, but it's just to tell you that the structure is exactly the same. You have critical condition for the Lagrangian of your fluid, and you add here contribution of each irreversible process, viscosity, heat conduction, etc. And each time is the thermodynamic flux paired with the thermodynamic force. For instance, entropy flux, gradient of temperature, matter flux, gradient of chemical potential. But the temperature is a time derivative of another variable, this thermal displacement. But at the end, the variational principle tells me that this is the temperature. Similarly, for this is the chemical potential, etc. As we have seen in the finite dimensional case. So more complicated, seemingly more complicated, but same structure, same abstract setting. So if you compute, you get the equation. So you can really do it by hand. Critical points of these gives you the full PDE of the multi-component fluid with heat conduction, diffusion, and chemical reaction. Okay, so to conclude, let me mention some possible further development. So one development is modeling, right, in physical systems. So one aspect that I'm very interested are the modeling of geophysical fluid dynamics, which are essential for atmospheric and oceanic prediction model, for instance, for weather or climate. And in this area, very often you have to use approximations of the complete equations of motion. And very often these approximations kill the thermodynamic consistency of the model. And this can have a bad impact, for instance, on the long-term accuracy of these models, for instance. And some of these approximations are obtained by imposing some thermodynamical constraints. For instance, the low Mach approximation impose some relations between mass density and entropy density, for instance. And it's hard to derive thermodynamical consistent models if you work directly at the level of the PDEs. But it's simple to do this if you work at the level of the Lagrangian. So if you do your approximation in the Lagrangian, not in the equations, and then apply the same critical action principle to the approximate Lagrangian, you will get something that is some model that is automatically thermodynamically consistent, which maybe you can achieve if you work directly on the equations, but generally it's very hard or impossible to achieve because you have to approximate terms in the equation in such a way that you save the second law of thermodynamics, which can be hard if you have some strange constraints on the system. So the result is that sometimes you have to modify the notion of temperature, etc. So this is some work that we did recently. And another area of where we think this can be useful is to discretize thermodynamic systems. So here I'm recalling why variational principles are useful for mechanics, to discretize mechanics. It's because when we discretize mechanics, for instance, even a simple discretization can have dramatically bad impact on the energy conservation, for instance, on the first law of thermodynamics. It can completely destroy the first law. But if you do it in a way that is structure preserving, then you will preserve a lot of conservation laws of the system, including, for instance, energy conservation. So this, in mechanics, this works well by discretizing Hamilton's principle. So, because for this reason, for instance, your scheme preserves the underlying geometry of the systems. For instance, a geometric structure like a symplectic form, for instance, on phase space. So your discrete scheme will preserve the volume in phase space, for instance, which is not the case for a scheme that you derive without having this geometry in mind, right? And so this is extremely well known for mechanical systems. You have important references about this here. So what about thermodynamics? So we think it can be useful too if we use our variational formulation to also build some thermodynamical consistent numerical schemes, for instance, for fluid dynamics, or we have in mind geophysical fluids like oceanic and atmospheric dynamics, in such a way that these schemes will automatically preserve the invariant or the entropy equation of the system, right? So this is the second area in which there could be some possible application of our scheme. Okay, so to summarize what we did, so main point, we extended Hamilton's principle to the case of non-equilibrium thermodynamics, and take-home message, it is a D'Alembert type of variational principle. And I like to present this diagram to remember how classical mechanics is included in non-equilibrium thermodynamics. And in a similar way, Hamilton's principle is included in the variational principle that I described. And something that I didn't show is the geometric structure associated to this. And so there are some geometric structure that are associated to our variational principle. These are Dirac structures, and that in some sense replace the symplectic structures of mechanics. So I'm just giving you some reference here. And I would like to, so some modeling that we did, and also an interesting aspect is the link between the variational formulation that we developed and some bracket formulations that have been proposed on the more on the geometric side as extension of Poisson bracket for Hamiltonian system. So there are two main kind of bracket formulations due to Kaufman, Morrison, and Grmela, and later by Oettinger and Edward Berries. And we can recover these brackets directly from our variational formulation. So it is a good, also good aspect, good unifying aspect for our variational formulation, that we can also unify some geometric structure that have been proposed. And we have also some work on the Dirac structure formulation of the thermodynamics. So, okay, so thank you very much. I leave you this sentence, and I'm happy to have your comments.
All right. I enjoyed greatly the talk. I hope Everybody was having a different take on it, as many people working in different disciplines. But yeah, let's open the floor for any questions that people have or may have occurred during the talk. Yeah, Shripad?
Hello, thank you very much for this very interesting talk.
Thank
So
you.
I have actually a very simple question
Mhm.
because in fact, I must accept the reality that I did not understand quite a bit of the variational part of it. Just it's my fault actually. But my question is that where exactly in your formulation are the fluctuations involved where there can be violations of the second law?
So this is in the variational constraints. Yeah, exactly. In the D'Alembert type of constraints on the variations that I use, this is where the second law is in some sense encoded. Exactly. It's like in D'Alembert approach in which the fact that the mechanical system has to fulfill some constraints is encoded in the constraints on the delta Q. For the non-equilibrium thermodynamics description is the same thing, right? The constraint that we use is there to fulfill the second law. Does it answer the question?
It's fine, yeah, thank you.
Okay, yeah.
I think, Shripad, did you mean more like the fluctuation theorem or?
Actually, that is precisely what my question was, but because I was not very sure whether I'll be able to put it in this finite time, because we have the violations of the second law, and it was somehow not clear to me. Either I missed something, or I'm not very clear how the violations in the second law, as determined by the fluctuation theorem for small space and small time, are captured by the principles which has been presented by the scientist here.
Ah, right. So I'm not there yet. I'm working purely in the macroscopic thermodynamics. That's an important point. Absolutely. Yeah.
So
All my examples are classical irreversible thermodynamics. That's where we are now. We are not yet including fluctuation dissipation relations and things like that. Absolutely. Thanks for the question.
Okay. I think that clarifies, yeah.
Yeah, good.
So just to clarify it for everybody, what Shripad means is that for microscopic systems, for close to quantum, there is uncertainty of time and energy, and you could have small like fluctuations that lead to decrease of entropy. But as François says, he is working in a macroscopic, which is a different domain, like the difference between quantum mechanics and classical mechanics. So I guess that will be the next level, the next step. Okay. Thanks for the question, Shripad.
Pleasure. Thank you very much.
Any other questions?
Terry, can you unmute and ask question directly to François?
Yeah, I have a question. So I have a couple questions. So it seems to me, François, that your approach relies a great deal on the difference between a Hamiltonian approach and D'Alembert.
Yeah, absolutely.
So I'm a big fan of D'Alembert. And I think, so part of it was in D'Alembert, as you were represented in, and there's a lot one could say about D'Alembert, but you were talking about the inclusion of natural constraints. In other words, you don't, in Hamiltonian, you can have everything symmetric, everything wonderful and conservation. But in D'Alembert, has to its basic description, there are some constraints. I mean, you don't have a description without constraints. Yeah. So it seems to me that that's going to be central to irreversible processes or to some dynamical development. So I'm just, I mean, maybe you could amplify on this the difference between the Hamiltonian. I mean, you make this lots of wonderful links between the phenomenological and variational stuff, but just focus on what we call the Lagrange Hamiltonian approach and the presuppositions of that approach, and then what D'Alembert does, which I don't think has those same presuppositions. Maybe?
So your question is, can I clarify a little bit the difference, right? Right?
So you asking me?
Yeah, exactly. What was the question again, precisely?
Okay, so the question is, I want you to give us 2 minutes on the difference between the Lagrange Hamiltonian formulations and D'Alembert formulation.
Ah, okay, right. Yeah. So in mechanics, right? So for the case of mechanics, in fact, if I go back to this picture of the field here, Hamilton's principle is an ordinary critical point condition. You have your space of fields that is, for instance, here, all the fields of the theory, and you compute the critical point of the action functional on this space of field with respect to all possible variations of these fields, right? So this is the nature of Hamilton's principle. So you have your path, your space of path like this, and you allow all possible variations of this path, as long as they start and end at the same point. For D'Alembert principle, you look at your mechanical systems and you look at what are the constraints on the velocity on this space, and then you allow variations in the action functional that only variations that fulfill the same constraints with the mechanical systems. So, for instance, if you have a rolling ball, you have a constraint on the velocity, then the constraint on the variations, I mean how you vary these curves, is the same as the physical constraint. So this is not that easy, I agree. It's a very subtle constraint, right? If I look once more on the slide here, you compute a critical point, but you only ask this functional to be critical in some specific directions. This direction is the direction of the constraint, which is not the same as computing the usual critical point condition in which you add the constraint as a Lagrange multiplier. It's a very subtle and important difference. I agree. It's very, yeah.
That's what I want. That's what I want you to clarify.
Right. Exactly.
I mean, not just mathematically, but conceptually, what's going on here.
Yeah. Exact. Yeah.
So can I examine that a little further? Very early on, and I don't remember which slide it was, but very early on, you're doing just the basic stuff, and then you go, okay, here's the description, and then there's this, I would call it a rotational or a secondary aspect. Can we just consider that 0 and get rid of it?
You mean the rigid body?
Before that, way early.
Here? Here?
No, go back. Well, that's, okay, yeah. Yeah, there. So that last term there is equals 0. What is going on there?
Last term, oh, this one.
Yes.
Very important term. So here, delta Q is the variation of the curve, but the space on which the action functional is defined is such that we know precisely the starting and end point of the curve. So when we take the variations of the curve at time 0 and at time t, delta Q of 0 and delta Q of t vanishes, right? Because we have no freedom here. So when I integrate by part here, when I evaluate this integral, mechanical momentums times displacement on the initial and time, I get 0. But
Right.
it is seemingly simple, but in fact, this term, if we allow it not to vanish, it has a main role, for instance, if we want to study the simplicity of the trajectories, of when we do neutral theorem also. This term is, here it vanishes, but in general, it plays a role. Yeah.
I think it does. Well, my thought is that I think it could play a very important role. And usually when you get into mess, you want to go back and look at your assumptions and your presuppositions. And this is one that I'm not happy with. So say I wanted it, that's not 0. I have to say that's not going to be 0 ever. What do I have to throw out? Well, I have to throw out the idea that I have a perfect location for the initial and the final point. Yeah.
Yeah.
So what is that assumption of having for calculus of variations that I have the initial point and the final point? That's great. As long as you have that, then you can eliminate this. But I think what you do there, and then I would go back to D'Alembert, because I think it has to do with the moment of inertia of the trajectory. And if you have the first point and the end points all very nice deterministic, there's no moment of inertia. And I think D'Alembert begins very fundamentally with what he calls a decomposition of motion. So he always has these two aspects to any trajectory. And one is a nice, if you get rid of the angular or the moment of inertia, perpendicular, then it's great, everything's mechanical. But he doesn't do that.
Yes.
I would encourage you to go back and read D'Alembert's treatise on dynamics.
Okay, great. Yeah.
He's very clear about what they're doing there, I think. Anyway.
Yeah. Okay, yeah, that's a great suggestion. Yeah, I agree. Few people pay attention to this last term, I must say. It's only when we start to discretize the variational principle that we realize that to prove symplectic properties, for instance, of numerical schemes, we need this term. That's it. That's very interesting, in fact. So, yeah.
Let me just make clear, is this a question about, Terry, about varying endpoints? When the endpoints are not fixed, but the trajectory, let's say if you have a complex system, you could have a change in the structure or reorganization, and then the trajectory start and endpoints can move, right? So that's kind of probably another extension of the theory, maybe, right?
Now, what I'm pointing at is that from the initial, what are we trying to do here? We're trying to understand non-equilibrium thermodynamics. We're trying to understand irreversible processes. And so when we eliminate a term like that, I'm thinking what we're doing, unfortunately, one way or another, and we can do it in terms of the initial final position or whatever, but we're locking ourselves into Lagrangian framework. Lagrangian Hamiltonian framework. And what does that mean when we're locking ourselves into that? Well, we're locking ourselves into conservation of energy and conservation of Noether's theorem. I mean, there's all these assumptions that push us into a mechanical framework. And I don't believe, with all the wonderful stuff that François has got here, I think he's into a lot of good stuff, that if we fix ourselves into a mechanical framework and adopt all those symmetries and conservations, we're not going to have any account of irreversible processes or non-equilibrium thermodynamics. That's where I'm.
That's really great feedback, Terry. And we have one more question. Velimir Elik, can you please unmute yourself and ask questions directly to François?
Yes, thank you. Thank you. Very nice talk. I have a question exactly related to this slide. So you assume that Lagrangian is of the form kinetic minus potential term. And can you assume more general Lagrangians, like which are not separable with this sense? Do we really need this form, kinetic minus potential?
It works for any form of Lagrangian, absolutely. Not necessarily of this form. I wanted in these slides to have a classical introduction. That's the only reason I had this simple form. But
so this is just an example, right? The discussion is general.
The discussion is completely general. For instance, if you do electric circuits or other systems, they may not have this form kinetic minus potential. They could be different. And we still have the same properties.
Mm-hmm. Okay.
Yeah.
Thank you.
All right. Any other questions?
So I have another question.
Yeah.
And it may be a suggestion, but I've been going back through Huygens and Leibniz and principle of variation, where it came from, how it developed, various divisions of it. And one thing that strikes me, there's a colleague in Germany who was pointing this out to me, but the 1/2 mv squared, which is supposed to be kinetic energy, and that's what's conserved or something like that. Well, you know, if you go back, there's this debate about mv squared in the vis viva controversy and so forth. And this relates to my earlier question too, because for Leibniz and Lavoisier and even Lazare-Carnot, they assume that all change has two aspects, a linear and a nonlinear. Okay. Now I would say linear and angular. Okay. A rotational and a thing. Then Newton splits them. He has the three laws, and then he has gravity for the angular. But there's a switch that supposedly, as far as I can tell, comes in with Coriolis. He says, oh, it's very confusing to the students to talk about mv squared, so let's just make it 1/2 mv squared. Now, when you do that, you put yourself into a strictly mechanical framework, and you lose what Leibniz and Lavoisier and Lagrange, Lazare-Carnot were talking about, this idea that there are always these two aspects. And I think that comes, Lazare-Carnot is my favorite. I've been translating some of the stuff, but he was a student of D'Alembert. And so what you see in Lazare-Carnot is very much the D'Alembert deconstruction of motion. He always has, you know, it has two aspects to motion. If you look at Lazare-Carnot, there's always a cosine, you know, there's this, and then there's a cosine angle up. And I think what happens, what we're doing when we say 1/2 mv squared is our kinetic energy. We're going into a, I would call purely linear concept of change. And we've eliminated, and that's where that term at the end gets eliminated too. There's no angular aspect to the motion. I would say, oh, we can add that in later. It's another component. But linear momentum and angular momentum are not automatically compatible, commensurable. I don't know. Is that helpful at all?
Okay, I see. Yeah.
Since you're French, go read Lazare-Carnot's Fundamental Principles of Equilibrium and Motion. It's
great. Thank you. This remembers also the case when M can depend on S, or the entropy or the temperature. This is also an interesting problem, but yeah.
The whole definition of energy is what I'm pointing at.
Yeah, exactly.
That's the problem. I mean,
yeah, exactly.
And you're never going to get a thermodynamics that's constructive and where the system evolves, as long as you've got, if you presuppose kinetic energy as your energy.
So I will encourage that everybody continue with the discussion in the future, because I think there are a lot of interesting questions and extensions and applications that could be done. And I think there was one question that's in the text, which was from that direction, which is, can that be applied to economics? I'm not sure, because I know that Lagrangian approach is a big part in the economic kind of financial optimization, Lagrange multipliers, but they're more of probably the other type of problems that you talked about. So
can I ask you, Georgie and Francois, something that bothers me about Lagrange, and that is, you know, he starts out very early on talking about principle of least action. And then he goes, and Euler goes, oh, wait a minute. There's least action, there's most action. So we're really talking about extrema. Okay. So all of a sudden there's an ambiguity here. So whenever I'm solving a problem using Lagrangian thing, I have to decide, am I going for a least path or a most path? Okay, and that ambiguity is there, which says to me that this is not generalizable for mechanics. It just says I have an inherent, ambiguity there. I can't decide whether I have a system. Is it going to go this way? Is it going to go that way? Quite different. Well, I can constrain it all over the place and say, well, the problem I'm trying to solve is the least problem. Let me give you an example real quick. Variable pitch props. You know those in airplanes? And you can change the angle of the prop. Now, when I'm taking off, I want maximum power. Okay, so I want my extremum power. And so I take off, get me up to proper altitude, proper velocity. Then I don't want the power. I want the efficiency. Then I want the least. Okay, so I've gone from a most to a least, and then when I land, I have to do some other reversing things. To me, that's a natural problem that suggests that if you take a Lagrangian approach, you got to go one or the other. I mean, typically. Does that resonate with you guys at all?
I think that's a great point to ponder and kind of like a good feedback for all of us. And I think it's the time to wrap up, Georgie. What do you think?
okay, yeah, as I said, that's what I was hoping for, that there will be, to use mathematical language, infinite number of questions, no matter what infinity means. And I think evolution and development and human creativity are open processes, so there is really an infinity, not just figure of speech. But that's the exciting thing about that. So I hope we could continue either via email or some other meetings, exchanging ideas with François and maybe his collaborators, and eventually post maybe some new problems or get interesting results and advance the field. And as I said, I'm hoping that his approach will help a lot the non-equilibrium thermodynamics and all the other sciences a great deal. So let's try to spend some time on that and popularize it and make sure that people know about it. Okay, so I'll stop here. Again, thank you, everybody. Thank you, François. It was an excellent talk here.
Thank you very much.
Thank you very much, Francois. It's really great talk. Thank you.
Thank you.
Hopefully we'll have more chances to meet. Yeah.
Bye-bye.
Okay.
Bye-bye.
Bye.
Bye.